Okay, let me take a little bit less thick. Yeah, quantum information, maybe. Yeah, perfect. Information and entropy. Okay, right? So, if you see quantum information, as you people are already going through, okay, right? So, let's understand about the second term, which is entropy. Okay, which this is the term we were coming across probably from our high school level, right? Come across from high school level, under which area it will we will be coming across is in thermodynamics. Okay, so in or I'll say while going through thermodynamics. Okay, let's connect that knowledge what we know because it's easier in that way. Okay, so thermodynamics, in thermodynamics we did come across the entropy. So what is entropy, by the way? Question is, what is entropy? Okay, doesn't matter whether it's a thermodynamic or anything. Okay, so we have known entropy in terms of the disorderness in the system. Disorderness. Okay, right? There is no orderness in the system. Something you can say mixedness. Okay, no order, no nothing. So that is actually mixedness in the system is entropy. So the example is simple example. You take a glass of water you take and start heating. Okay. What I mean is just take a hot glass of water. Okay, water is there and start heating. Maybe using some burner. Heat. What happens is the moment you try to do this, okay, what happens is once you start heating, the water particle which are getting heat, as the hot things always travels towards the top, so the particle starts traveling up. Okay, and they are not traveling in a nice pattern. Okay, they haphazardly travel. The hot particles like hot H2O molecules, let's say they have not disintegrated into hydrogen and oxygen, still intact as a H2O. Okay, I'm talking at that level. Let's say when they start disintegrating, in that case, maybe we will see hydrogen and oxygen emitting out of this hot water. We are not, as of now, let's say if it humidifies, okay, humidifies, or let's say it becomes vapor, the water molecule still goes as a hot water molecule intact. So that is what we are talking about. Okay, they are moving up haphazardly. No systematic way they are moving very fast. Okay, at that moment, if I ask you to check whether this hot water is earlier, when it is in warm or cool position, if you keep water in a beaker, okay, and you can see everything is stable. I don't see any movement in the water unless if I stir it, unless I disturb it. Okay, right? So this hotness, okay, the glass of water and start heating, the addition of heat, the addition of heat creates a disorderness in the system. Okay, what I mean is as hot particles cannot stay at the bottom, they start going up, and cold particles start coming down. So you can clearly see when you heat it, you see clearly something is moving up and then circulating. Okay. So here the disorderness, the no orderness is there. So we would say earlier orderness was there, disorderness was very low. Okay. As you increase the disorderness, the entropy gets increased. Okay. Addition of heat creates a disorderness, and you can say entropy got increased. You can say entropy got increased. Okay, so usually it is referred by letter S. Okay, right? Fine. So we'll say entropy at a given temperature, that is entropy at a given volume, given temperature, given pressure. Okay, okay. So volume, temperature, and pressure. This is what we come across in our high school level. Now, let's connect this to the area which we wanted to look for today. Okay, right? What is that is the quantum information we are going to have. Okay, some information we are going to have. Is that information is nicely structured or not? Okay, so objective for us is to connect, okay, connect the concept of thermodynamical entropy. You see now, concept of thermodynamic entropy to the quantum information theory. I'll say quantum information theory. I want to know about the quantum information. Okay, this is what our objective for today. Okay, right. So the question is there any entropy associated with information? We'll not go to quantum information. Let's stick to information as of now at a very early stage. Okay, right? At a very early stage, let's try to understand, is there a entropy in the information, or I would say, is there any disorderness in the given information? That is what I will ask my question. Okay, so the answer is yes, we can associate. That's what the yes, it is done by, associated by Claude Shannon. Okay, right? When did he do? He did this in 1948, just after our independence. Okay, right? So what he did is, he did give, okay, he gave a mathematical theory of communication, or some mathematical foundation he gave. He has given a mathematical foundation to address information theory. Okay, information theory. Okay, what I mean is, this has got everything. Okay, so let me jump to the slides, and I'll just show you. Right, so yeah, right. So information measures the reduction in the uncertainty. Okay, right? Uncertainty. Now he brought in a new word, like, or let's say we will bring out new word, uncertainty. Uncertainty means something is not certain. Okay, right? So let's say if you ask somebody in the, let's say, a railway station or a bus stand, who doesn't know whether particular train has come and gone. Okay, you can ask him, right? You can ask him, is this train is still there or gone? He would simply say, right? He would simply say, no idea, right? So he has no information about it. Okay, right? So he has no information about it, which means, right? Uh, this information is uncertain. Very good. Fine. So now, let me, yeah, information measures the reduction in the uncertainty. The more uncertain an outcome, the more information is gained when it is revealed. What I mean is, to represent the uncertain information, I would be needing lot of description. Okay, so lot of description means everybody needed an individual description. Let's say if I have a set of students, all are alike in one way or the other way, can simply represent any of them in one shot. Okay, if if in case every individual is different, in that case, I would be needing to specify who is what and what is the description of each person. Okay, it's completely different. In that case, what happens? I need to have more amount of data I should use, more amount of memory I should use to represent all of them. That is what the information is all about. The more uncertain and an outcome when I make a measurement, the more information is gained when it's revealed. So basically, different things needs different ways of description. Okay, so Shannon introduced the entropy information, a mathematical theory of communication. Okay, and he said, right, few key things, or he tried to address few key questions. What are they are? If you see key questions, how do we encode information efficiently for storage and transmission? Okay, just like entropy is there in thermodynamics, here also information has to be stored somewhere with orderness. Okay, if everything is in orderly fashion is there, less amount of data I would be memory I would be using, and also for transmission would be very easy for me. Okay, right? I'll tell you one simple example. Okay, for electronics people would definitely appreciate that. What I mean is, okay, right, let's take a Fourier transform. Okay, so consider one analog situation, analog scenario. I will say scenario. What I mean is, let's say I have a sinusoidal wave. Let's say I have a sinusoidal signal. Let's say some f of t with respect to time. If I have, it has a nice periodic behavior, something like that. Okay, it goes as temperature increase. It goes like this. Now, to send this information to somebody, let's say it's an experimental data. I don't have a theoretical information in some kind of sine function or something. Let's say what I have a tabular information. Let's say for every given t, what is f of t I have. So there are so many values. Let's say some 200 by 2. That many number of data points I have. Okay. Now, if I want to communicate this to somebody, what I do, I have to prepare the table and send the table to the somebody. Now the question is, I'm using a lot of resources here. Okay. So somebody thought this particular scenario, why can't I change it? Okay. The effective way of transforming or transporting, let me say transporting the above information is by using, I would say, Fourier transform. What is that is? Transform. Okay. Find the Fourier transform of this particular function, which is Fourier transform of f of t is going to give me a function capital F with respect to a variable angular frequency. By the way, what is angular frequency? It is 2 pi by 2 pi mu is the angular frequency, where mu is 1 over t. Okay. Now you see, I converted a Fourier, like a f of small f of t to capital F of t using a Fourier conversion, Fourier expression. You people know, we will come across this Fourier transform everywhere. Now if you see, if you plot f of omega versus omega, you know what you get is, you are going to get a one single point you are going to get. Okay, let me exaggerate. What is that? It is something like a small thin very sharp peak. This is what you are going to see when you are going to take a Fourier transform of, okay, Fourier transform of a very very large quantity. Let me draw it neatly. Okay, fine. So what is this point? At what point it just gives you? Let's say omega naught is the angular frequency of the signal f of t. Then we see f of omega peaking at omega equal to omega naught. You see, now I only transfer one single number. Let's say that single number to be, let's say, some 50 hertz. Okay, 52 pi into 50 hertz angular frequency. Okay, let me do that into 2 pi. Okay, so this is the angular frequency. I just communicate the entire information in one shot. You see, earlier I have to send the entire data of table. Now I will only send. Now I am able to send entire tabular information whatever I had earlier using a single omega value. Okay, very easy, right? So people are looking after this kind of a things, getting to reduce the amount of memory usage so that resources could be like we can save our resources. Okay, so let's jump into the PPT again. Okay, so the reliable, okay, the how do we encode information effectively for storage and transmission means I should reduce the amount of resources. Okay, so that is one thing. At the same time, the reduction should be in such a way that transmission happens effectively. Okay, so Claude Shannon tried to address these things using his mathematical foundation. Okay, right? So that is one of the key observation, a key question I'm trying to address. And another one is reliable communication. How do we do reliable communication? communication is we should know how to transmit quantum information. For example, here classical information in case of classical communication, we should be able to do reliably through even we have a noisy communication channel. Okay, ideally we think that our information go intact without being disturbed. In that case, fine, I can keep quiet. Whatever I created, I assume that it goes to my second party or somewhere I'm intended to send, it will go undisturbed. But that is not the case every time. Okay, there are disturbances. For example, if I send the information through a cable, as it progresses, so because of the resistance, the energy is lost. Okay, right? Because of that, the information is lost. When I take an optical communication itself, I am sending light through some optical fiber. So through optical fiber, what happens? As the light progresses through this dense transparent medium, light also loses its strength. It's all about electromagnetic radiation. It's all about electric field vector which is oscillating, magnetic field vector which is oscillating. They're oscillating against some medium. Okay, once they're oscillating against some medium, they're doing some work. As they're doing some work, they lose that energy. As they lose energy, obviously I would lose the chance of getting the information intact at the other end. Okay, right? So we should look for some reliable communication. How do we transmit information without being compromised, even though there is a communication noise in the channels? Okay, right. When it comes to quantum, what we need to address by taking a page from channel is information encoded here in our case is in the form of quantum states. Okay, I'll explain what it is. And information is stored in some quantum states which requires entirely, okay, it requires entirely new entropy measures and new approaches. Okay, why I'm saying in 1948 probably Shannon might have not thought about applying his theory to a quantum information. He may not be thought about there will be a quantum communication channel or quantum computing channels will be there that may need to be addressed using his entropy mathematical foundation. That's why we did not go through. What we will do, we will see what Shannon has done for a classical information case, and we'll try to replicate or mimic that to a quantum information. Okay, now as we see, let me see how it is being done in a classical case. Okay, so here I have the next slide. Okay, let me concentrate on the left side. Okay, so there is some overlap. Okay, so that I'll take care of later. If you see here, classical versus quantum information, how it is done, we have seen it in very early stage, very first session, I think. I did discuss about how classical memory is being realized, how a quantum memory is being realized. Classical memory is being realized by what? Classical memory is being realized by, okay, using classical memory is being realized by using something called transistors. Okay, right? So let me take a colored pen or okay, red pen will do the job, I think, for us. Yeah. So the classical information bits 0 and 1, maybe white color is better, I think. Yeah, let me choose white color. Okay, well, yes, 0 and 1 are realized in terms of transistor being in off and on mode. Okay, so that is how bits 0 and 1 are realized on a given transistor. Okay, right? So now here if you see, information is classical information is carried by bits 0 and 1. Okay, the uncertainty is there. The uncertainty means what? Let's say I intend to keep the transistor in on mode. Okay, means let's say I want to transistor to be in on mode. Because of the problem in the transistor, okay, it becomes off. Okay, the issue, let's say there is some issue. Okay, so what happens? 0 becomes 1, which I don't want, but it become, because of that there is a problem. So let's say with some probability p, it becomes 1 to 0, or sometimes 0 to 1 it becomes. I can't certainly say, see, whenever things are certain, 100% probable, like with 100% certainty I'm saying means, with 100% probability I'm saying things are certain. Something is there on my table, it is going to stay on my table. Okay, but then in the case of transistor, let's say I'm not sure about all transistors are working perfectly or not. In that case, if I put a transistor in the off mode, sometimes it becomes on, sometimes it becomes on to off. Okay, what happens in this case is I'm not certain. Okay, so some deterministic measurements need to be made, okay, to get some outcomes out of it. Okay, so to know about it I have to make some observations which has to be very much deterministic, means very much certain. Okay, fine. So this is what the classical information it could be. Now in a case of classical information, how it is being addressed is classical information, dealing with the classical information, dealing with classical information. How it is done is, let's say consider 0 bit, it stays 0 bit with some probability. Let's say it converts from 0 to 1 with 1 minus pre-probability. Sorry, let's say pre-probability it converts. It remains with 0 as it is with the 1 minus pre-probability. Similar story for 1 also. Okay, 1 remains intact, but it may get flipped to 0 with a p probability. With 1 minus p probability, it remains to be intact. Using the probability, using the probability theory, we could okay, let me we could we could deal with the okay uncertain situation. What is uncertain? Sometimes when things are not stay deterministic or certain in that case. Okay. So this is how classically using probability theory we deal with it. Now, in the case of quantum theory, in the case of quantum information, by the way, what is quantum information for us? Okay, how do we store the quantum information? Is we use okay, we use quantum qubits to store the information, okay, in the form of, you see now I'll say in the form of probability amplitudes. Okay, this is called amplitude embedding. Means using the amplitudes as a means, we are going to store the information. Example, if you just take quantum state psi in a Dirac notation is equal to alpha 0 plus beta 1. Here, the alpha and beta are the probability amplitudes through which we store 2 bits of information in a given quantum qubit hardware. Okay, so quantum qubit or quantum bit, in short, it's a quantum qubit or a qubit. Okay, stores 2 bits of information on same unit. I will say same. Okay, what these units could be? Unit could be a single electron in a box, or unit could be a photon. Okay, a flying qubit. In terms of photon, I may have, okay, a photon case. I may have photon having horizontal polarization and vertical polarization. Okay, so I will say H and V are polarizations of EM wave associated with that particular photon. In this way, we will store the information that since I'm using a quantum hardware to store these 2 bits of information, I'm calling it as a quantum information. Okay, so now there is a slight change when it comes to classical and quantum. What is that slight change is? Okay, what is that slight change is? Here the alpha beta are not the numbers which I can take whatever I want. Okay, what is that is important? I will say put a star, most important. So the probability amplitudes possess, I will say, possess constraints. What is that constraint? Absolute alpha square plus absolute beta square is 1. What I mean is, if I sum the probabilities, always remember the probabilities when you sum, at the end it should lead to 100%. The same story here, alpha square plus beta square is 1. Okay, so I can't have any alpha beta. In that way, the embedding information is slightly correlated to each other, but nevertheless, we can still store 2 bits of information on it by using some tricks. That is what people are doing from quite some time. Okay, very good. Now, there are some issues with the quantum information. What is the issue is, okay, right? Some limitations, I would say limitations that could be converted into advantages. Okay, you see now, I'm not just saying the limitations, say those limitations could be converted into advantages. What are them is measurement of a quantum system. Measurement of a quantum system or a quantum state, I would say. Okay, right? Destroys the quantum state. Destroys, or I would say collapses the quantum state into a classical form. Means no more that ambiguity of alpha and beta together existing, no more happens. It is going to stay only one number. Okay, that is the one of the constraint, one of the limitation, but which could be definitely converted into advantage. How are we people doing? They are using, okay, so advantages comes from what? Number one, we are using superposition here to represent the information in terms of 2 bits. You see, psi is equal to horizontal plus vertical polarization superposition, and I would say quantum qubit could be in the 0 and 1. That is a superposition for you. This superposition enables you to keep the or store the information in a rich fashion through this quantum state combination. Okay, so the superposition could be, quantum superposition could be various states I can have. Let's say alpha 0, alpha 1, and so on, alpha n. Okay, so this is a n-dimensional Hilbert vector space, which could store n bits of information, okay, on one state or one vector. You see, this is power of superposition. Using that, I can see everything in one shot. So the even entire information I can store it into one quantum state which captures every information. Not only that, you remember there is one more advantage of quantum information is, let me take that advantage, is entanglement. Okay, what is this entanglement is? Within the states, remember how I am going to do. Okay, let's consider 2-qubit states. 2-qubit means there is one atom, okay, another atom, which is, let's say, A0 plus beta 1. If you put them together, what I'll have? Two systems, alpha A, alpha B, A beta. Okay, just a minute. Sorry, BA, that is BA. B. Let me neatly write down. Beta A plus beta B. This is the state I have when I take two systems together. Now, interestingly, what I can do some processing, okay, such a way that alpha B and beta A could become 0. When they become 0, what happens? The new quantum state which is formed, I would now say ENT, not ENT specialist, it will say entanglement. Psi ENT would be, okay, this time I will say alpha 00 plus beta 11, okay, beta 11 get, this is the state I am going to get. Okay, so do some processing means some unitary operators or combination of some unitary guess. If I do, I am going to get entangled state. In this way, what I am doing, 4 bits of information is there anyway. I am creating where a correlation is being created between the data points. So it's not any correlation, very powerful correlation. If you do one thing at one location, even if you don't do anything in the other location, whatever happened with this first thing, it should be able to induce a change in the second thing. That is a very powerful thing. So this is entanglement is a feature comes in the case of quantum information, which is in fact an advantage. Just like a superposition, entanglement is an advantage where correlation, because of the correlation, some change happening at A, change induced at A could result in some change even at B, okay, irrespective of anything is done at B. Okay, very good, right? Even though I don't do anything at B, still I can see some change in B if I have an entangled state like this. So in the quantum information, this facility is there. So how to tackle if I use this quantum hardware to store the information, how to tackle this, that we should understand. Okay. Now let's jump back into the PPT. Okay. So let me go to the next part. What did Shannon give entropy wise? Okay. So classical wise, what did he talks about? Okay. Right. Let me enlarge this for your convenience. Okay. Now you can see clearly. If you see here, okay, yeah. If you see here, Shannon introduced entropy as a measure or a fundamental measure of uncertainty for a random variable, okay, right? Providing the mathematical foundation provided mathematical foundation for information theory. What I mean is, let's say a random variable is given to you. Let's say we have a dice, 1 to 6 dice are there now, all 6 faces. Each face is given and a dot. So there is a face with a single dot, 2 dot, 3 dot, 4 dot, 5 dot and 6 dots. So there are dots with a quantum information, sorry, classical information. Okay. So what you can do is, you see, you can just pick particular dot by just rolling. So let's say if you roll, oh, it will just fall into particular form, right? Now the question is, what is the chance of that particular form is coming, whether it's a 1 or 2 or 6 coming? What is the chance? You can simply say 1 out of 6. If it is a very fair die, remember, a fair die means anything is possible among the 6 faces. Okay, so likewise, there may be a fair coin. So in this case, let's say in the fair die case, my random number is a chance, let's say random number I want to pick. Random number. Okay. I'll just take an example. Pick a random number from 1 to 6. Okay. 1 to 6 I want to pick. Now to pick a number from 1 to 6, okay, I can close my eyes and pick. But the thing is, my brain is working and my brain has some connection to some number, so it tries to pick that number. So just to avoid, I want to make it more random, no relation to anybody, any previous number or later number. What I will do, okay, use a dice with 6 faces, each face having a dot, okay, or multiple dots. Okay, so dot running from 0, 1, 2, 3 and so on. Okay, right? So these dots are there. Now what is the chance of, okay, question is, what is the chance of getting a particular dot? Let's say 3 dots. Okay, you would say the answer 1 by 6, because well, there only one situation among the 6, so you have a probability 6. So probability of getting 3 is 1 over 6. Okay. Now see here, the random number is from 1 to 6. Now to measure the chance of this random number, okay, what the probability or the uncertainty with this case, I can use that as a entropy measure means if I pick every time the 3 means the information is no uncertainty. Information is in orderly fashion. It is coming out when I pick when I roll a dice. But here that case is not there. Information is uncertain. Any information can come. So I need to mention all the cases. So the measure of uncertainty here is the measure of the uncertainty, or you can even say probability, okay, is by Shannon entropy. He gave a mathematical expression for that. What he said, h of this random number x is equal to probability of that x having various values, but I am talking about p of x log, so in this case log 6 of x. Okay, so there are 6 scenarios, so I'll take with a base 2. Okay, right? So let's take another situation, a pair coin. Okay, in that case the Shannon entropy would be p of x log 2 of, I'm sorry, this is a p of x. Okay, so this is how he interpreted uncertainty in the case of information, and he gave a mathematical definition and expression for that. Okay, so the interpretation is this represents the average number of bits needed to encode the outcomes optimally using the most efficient encoding scheme. That is amazing, right? It's not just a mathematical expression, the entropy measure, which is also going to tell you how many number of average bits needed for to encode that outcomes optimally, whatever outcomes you pick, okay, to encode them optimally, you would be needing this much number of bits. Okay, we'll come to that one specific scenario now. Okay, and he even said the units measured in bits when using logarithmic base of 2, providing intuitive connection to a binary information. What did I give you? I gave you a hexagonal scenario where there is a 1 to 6 options are there. In the binary case, there are only 2 options. Rajeshwari ji is asking a question here. Let me go through that question. This entangled state must be maximally entangled. Very good question. Okay. Maximally entangled or partially entangled is a question first. Okay. When I take 2 systems, atom A, atom B, where is that? Here. So these are entangled to a maximum extent because they are the only 2. If I say they are entangled, I'll say they are maximally entangled. Let's say I'll take 100 atoms or 100 entities out of 100. So there are 40 guys who are entangled, 60 guys are not entangled. In that case, I would say the entire system is partially entangled because there are 60 of them which are not entangled. Even I can do one thing. I can just pick the entangled part and only do the computation. If not, I eliminate the unentangled ones and only deal with the entangled ones. Those are the ones which are useful for me and interesting for me. I'll do that. Okay. I hope I answered your question, Rajeshwari ji. Yes, the 2-qubit situation or entangled situation which I have chosen is strictly maximally entangled. Okay, then coming back to my slides. Okay, so measured bits when using a logarithmic base 2, providing intuitive connection to a binary information here. Okay, in the expression which could be converted into any form of the situation which we can take. Okay, right? So in the case of deterministic case, means let's say there is no probability there. There is no uncertainty there. In that case, what happens? Let's take in that situation. Okay. Right? What is mean by that? Let's say I have a die. Okay. On all the 6 spaces, I have only single number. Okay. Right? Or let's say there is a coin. On both sides, there is a head. Like say Sholay. Okay. So in that case, the probability is 100% of getting any one of the situation. I get head every time, 100%. So what happens in that case? What is the entropy? Entropy is 0. There is no uncertainty. Okay. Very good. So let's say a biased coin. I will say a biased coin having head on both sides. Okay, where probability of getting head is 1. So the entropy is, I'll say head. Okay, just for confusion, the entropy of getting a head is 0. Okay, entropy in the sense, the uncertainty, is there any uncertainty? Like if somebody will ask, will you come? Will you come to a meeting? Do you have any uncertainty about that to come to a meeting? If you're certainly yes, you say no, I will absolutely come. There is no uncertainty. Okay, right? So there is a situation I can have maximum entropy. See, I just saw minimum entropy, and there is a chance of maximum entropy also. Okay, what is that is, if you have a uniform distribution which can yield a maximum interest in entropy, means greatest uncertainty. What I mean is, okay, example, okay, 6-faced dice, okay, has maximum uncertainty for any variable to take, okay, to get one particular, okay, face when rolled up. Okay, when you roll out a dice, I would say one particular face is a maximum, means there is no situation where there are two faces with the same number. That is not there. So it is all the numbers are of equal probability. That's what they say, uniform distribution. Uniform distribution. Okay, so that is how Shannon brought the nice mathematical interpretation for quantum like any information to be quantified when it comes to its orderliness. Okay, so let me go to the properties of this Shannon entropy. Okay, so we'll just have a quick 5 minutes break. Meanwhile, please take a break and we'll come back. Okay, I guess we gave a break at 5:42, and then it's almost 5 minutes crossed. We'll start. Okay, then welcome back, everyone. Yes, we'll start, restart. Right, we are going a bit slow, so we'll go a bit fast now. Yeah, there is a question by Bharat. Okay. Oh, sorry, it's Bharat ji is actually answering. Okay, so regarding quiz 1, quiz 2, and other quizzes, please keep checking the canvas. You will be getting updates there, so you can accordingly you can go ahead. Okay, right. Now we just saw how did a mathematical description of uncertainty in the information. Let's say there is a random variable I want to pick. There is uncertainty in getting its outcome values. That is a very good means for me, okay, to understand what is this entropy is all about. So Shannon actually mathematicalized or give a mathematical formula in terms of probabilities involved there. Okay, and now what is this expression? Is there any additional thing this expression has? You can see here the properties of the entropy. Okay, the Shannon entropy, the properties are, the one is the entropy of any random variable for all the random variables. Let's say take any random variable, a fair random variable. Remember, entropy is always going to be a positive quantity. Okay, right? So it can be zero. Remember, it can be zero. We just saw in a previous case situation. Okay, but it is always positive. That is one property. And number two property is, it is, number one, non-negativity. Number two is, it is going to be maximum for a uniform probability distribution. What I mean is, like say earlier, if 6 face dice is there, when I roll, if the chance of getting one of them is same as chance of getting in all the other 5 situations, means I might get 1, 2, 3, 4, 5, 6. All of them are equally probable. Then I would say uniform distribution. Interestingly, for that uniform distribution, okay, entropy is maximum. What is the value? It is the value in the case of fair coin. It is just the log of 2. Okay, right? In the case of, okay, in the case of any other dice or anything, accordingly we have to see. Okay, now, okay, the next thing is, just a minute. Okay, so the next thing is, if you just take entropy of two systems, let's say I have a fair coin, let's say I have a fair coin, and I have a fair dice. I've said dice, not die, dice. Okay, one is corresponding to random variable x, other one random variable to y. I know a h of x, I know the h of y. Okay, now if I know how much entropy information is there, how much disorderness is there when it comes to a dice, when it comes to fair. Is there any way I can find out what is the overall entropy with respect to this kind of independent variables or independent random numbers? It's very easy. You just add them up. Additivity is possible when it comes to the pair random variables. Okay. So what you do, you just take one of them, add it to other one. Straightforward. Very good. Right? Remember, there are two independent variables. That is very, very important. In independent variables case only, you can just add. Okay? Where when they are dependent, you will just come down. You can see for the dependent case. What is that? In the dependent case, let's say, okay, what is the dependent scenario is, now I have a fair coin and a dice. Now what I will have is, let's say I toss a coin. If it gets ahead, then only I just roll a dice. If not, I will not roll a dice. That is one scenario. If I toss a coin, if I get head, I will roll the die twice. If I get tail, I will roll the dice only once. So if that kind of an interconnection is exist between the two random numbers, okay, right? So in that case, what I will say, they're actually interconnected. Let's say X is a fair coin. The result of X taking head dictates the Y, whether Y to get some value or not. Let's say if I get X is tail, Y is straight away 0. You know why? Okay, you know why? Why I'm not going to die? Toss that dice, roll a dice. Okay, so you can do other way around also. What is that other way around? Okay, let's say I roll a dice. Whenever a dice gives me an even number, only in that case I will toss a coin. Otherwise, I will not toss a coin. Okay, so that kind of a connection if you keep, now what happens? So there is a relation exists between the two random variables. So they are like a dependent case scenario. So there you can't just simply add the overall entropy. What should I find? First of all, you should find what is the entropy of given variable when the other variable onto which this is variable is depending on. Okay, so in this way it's like a conditional probability kind of case where entropy of X for a given Y plus what is the entropy of Y you should find. Then if you add them, you would get overall entropy associated with this kind of a joint scenario. So this is actually called a chain rule. Okay, that also is given. Next, there is something called concavity, okay, or concavity. Mixing property distribution always increases the entropy. It is just like I have nicely ordered water. Okay, I have a ink in the another bottle. If I add them up, it is going to create a much more disorderliness in the mixed, the ink filled water mixture. So that scenario, if you just take in the case of information, mixing probability distributions means two things which are uncertain. If you mix them up, the uncertainty is going to increase to a much more higher extent when I do this. So that is what concavity is saying. Okay, so entropy is always increases. That was the first, the non-negativity in the case of that. We'll see that. Okay, now these fundamental properties make Shannon entropy a robust and and intuitive measure for quantifying information content in classical system. Okay, so they are not just any mathematical descriptions. It is going to help me to get more insights in the information, whether it's a classical, even it is a quantum. We'll come to quantum later. Let's go further. Okay, so it is always best to take a very simple example. From the example, let's try to analyze what is this H Shannon entropy is capable of. Okay, here I have taken a simple fair coin. Okay, as we know, probability of getting a head and tail both is half 50%. Okay, Now, if I have to calculate what is the entropy associated with this a fair coin when it is tossed, okay, so the entropy comes with a minus sign as we have seen in the previous expression. What is the probability of getting heads? 0.5 log of that 0.5. As you know, the entropy of any given x is summation over x, probability of x log to probability of x. This expression, you know, you simply substituting as per the expression. As you substitute and if you measure, right, if you see half of log half plus half of log half is 1 log half, okay, right? So 1 log half, which is 1 into log 1 minus log 2, okay, right? Fine. So the minus of log 1 minus of log 2, so log 1 is 0, minus of minus is plus, so log of 2, by the way, it is base 2, which is equal to 1. I got that answer. So the the uncertainty, the Shannon entropy of this fair tossed coin and its corresponding random variable is 1 bit. What is it? It's a maximally having entropy. Means it's a perfect uncertainty exactly yields 1 bit of information. Okay. For example, let's say I have a biased coin. Other way around. What is the bias I'm going to say? I will stick some kind of a weight, let's say on the tail side. Some weight on the tail side. When I toss a coin, always I get a head. Only some 10% I will get a tail. Okay, in that case, that okay, the value of probability is probability. Just a minute, I'm sorry with that. Okay. So the probability of heads is 0.9 and probability of tail is 0.1. In that case, if you just calculate the entropy just by substituting those values, it comes out to be 0.47, which is much less than the previous scenario. Okay, remember it is positive by the way. So this would tell me there is a strong bias that reduces uncertainty in the information content. Okay, right? So here in this particular case, up to 90% I can say there is a orderness in the system, only 10% is there disorderness in the system. Okay, right? So the key insights here is more biased distributions have less uncertainty, resulting lower entropy values. You see, earlier entropy is 1, now it is just less than half. The relationship between the bias and the information content is fundamental to efficient coding. Very important. So if you know the relation between how much bias is there, okay, right, and information content between that you can have a efficient understanding and efficient coding you can do using that kind of a means. Okay, right? So Shannon entropy not only just gives you insight, it would allow you to even do information processing much more effectively. Okay, right? So that is one. Now talking about the digital communication or any communication using classical, okay, right? So yeah, there is a question by Keshav Rao ji, concavity example and chain example. Okay, they're asking for a chain example. Okay, so both the cases. I just did give you that example. Okay, let me come back there. The example for a chain case, dependent case, what I gave you, I have a fair coin, I have a dice. Okay, now I roll a dice, sorry, I toss a coin. Only when I get head, that time only I'll roll a dice. Otherwise, I will just not roll a dice. Okay. So let me take that example, chain rule. Okay, example for chain rule between two random variables. Okay, now let's say, I have x is a random variable. X is a random variable associated with a coin, a fair coin. Okay, similarly, y is a random variable associated with, just a minute, associated with, okay, a fair dice. Okay, now the condition I'm giving you is, I'll roll a dice. The situation is, roll the dice. If you get, remember, if you get y is an even number, then toss a coin. Otherwise, don't toss. Okay, now you see, only when y is going to be 2, 4, and 6. If I get 2, 4, 6, then only I toss coin, means I will get coin is going to be, x is going to be either 0 or 1. Otherwise, okay, otherwise I would say, right, always it is going to be 0. Right? Okay. Now, if I get y equal to 1, 3, 5, then don't toss. X is just 0. Okay, it's like always head. Now, is this situation, okay? In the first case, if you find the probability of getting 2, 4, 6 is equal probability. In the second case, probability of getting 0 every time or sometime is actually connected to 246, the y. Okay, so the probability, overall probability or overall uncertainty with respect to x and y is actually the uncertainty or the disorderness or the entropy in the x provided y plus uncertainty or like entropy in y. This is a chain relation. You can just cross check that. This is a chain rule for you. Okay. And what about the other situation? The concavity, sorry. Concavity. So what is the concavity is? Let's say I have two random variables. The two random variables are there which are independent. There is nothing. Okay. Now concavity. Concavity. I'll just take the same two examples. This time, again, take a fair coin and a fair dice. Okay. This time, they are independent. They are independent. What I mean is, whether I rolled a dice doesn't matter with whether I tossed a coin. Whether I tossed a coin doesn't matter with the roll dice. So in this case, what is the chance of x value taking any, the x has possibility to have 1, 2, 3, 4, 5, and 6. Okay, right? I'm sorry, this is y, in the y case. And x case, I have 0, head and tail. Now, whether I got head doesn't matter with what the y value take. So in this case, the entropy of x, entropy of y has no relation between each other. So which means, what is the overall entropy with both the variables? I just simply add them up. I don't want to even bother because they are not related. So this is actually concavity. So a simple, only if I have two independent variables, independent, then only I will have simply addition, that is called concavity. When I have dependent situation, dependent, in that case, I will have a relation, which is very, very important to have. Okay. I hope I answered your answered your question, Kesarauji. Okay. Let me get back to my presentation quickly. 1 minute. Okay. So this scenario. Okay. Next one is there any other metric or some quantifying technique which can also be used to represent uncertainty in the system or entropy in the system? Luckily for us, there is one more person's the entropy named after another person, von Neumann entropy. Okay, the quantum generalization of Shannon entropy. Okay, designed to capture the information content of quantum states through the density matrix. And so far we are dealing with the classical scenario. Now we are jumping into the quantum scenario. In that case, there is a way I can just generalize the Shannon entropy into von Neumann, another entropy named after von Neumann. Okay, what is that is shown like von Neumann entropy with the S of rho. Now I am not talking about a random variable. I am talking about a density matrix associated with that particular quantum state. Remember, now I'm talking about quantum information. So I'll have rho is the quantum density matrix or a quantum states density matrix. I am going to take, in that case, what is the entropy in that particular quantum state information? S of rho is equal to minus trace of rho into log p, where log is, okay, depends on what kind of a scenario I'm talking. So let's say right now it's a natural logarithm or log of base 10. Okay, minus trace rho of log rho. That is an expression for a von Neumann entropy. Okay, now let me use my quick recap for the quantum state. Now, okay, as we know, if I have a quantum state, a single entity or a single atom or a single electron or a single photon, this is how I am going to represent that using a quantum state. A quantum state. Okay. Now, if I have a collection of many such entities inside a box, okay, we initially presume that all of them are alike and all of them are, let's say, if all of them behave perfectly alike, same way, then we can represent them using rho. Okay, very good. That's the job for us. But unfortunately, the ideal scenario is, okay, ideally, which is not possible. What I mean is, there is a group of something which behaves like quantum state psi1. There is a group of some atoms, quantum state psi2, psi3, and so on. There are multiple groups. So there are groups up to psi n, okay, which is not possible. And there exists, okay, roughly, I'll say roughly n groups, each behaving as like there are groups in each group, okay, behaving alike. Okay, in each group there is a one kind of particular groups. So now, okay, now the question is, how do you represent the entire group in one shot? That is a question you can ask. Earlier, everything is represented by one quantum state, psi, okay, right? A group of quantum system. We are talking about group of quantum systems. In that case, how to tackle, okay, right? Okay. So now, luckily for us, there is a way. There is a way. What is that is? There is a way which is density matrix. Okay. Okay. By the way, what is density matrix? Rho is for a given quantum state. You take a outer product with a Dirac notation. You are going to get in fact. Okay. What are you going to get? You are going to get a matrix, you see, which is alpha absolute square, alpha beta star, beta alpha star, beta absolute square. So this is a matrix for you. This matrix, if you see, the diagonal elements of the matrix is probabilities. Off diagonal elements are polarizations of the quantum state. So is there a, using this density matrix, we can represent the entire collection of all the atoms. How? We can say now we can represent the entire group of atoms above. You see now by rho total. What is the rho total? Is summation over. Okay, I'll come to summation later. Maybe I'll write individually so that you people understand. There is a rho 1. What is the chance of given atom falling into a particular group? Rho 1 plus there is a rho 2. What is the chance of given atom falling into a particular group? Rho 2. So on Pn rho n. What I mean by that is rho total is equal to summation over I pi rho I, where rho I is simply psi I outer psi I. Okay. You see, in one shot, I represented all the group of atoms. Now you see here there is a greater mixing of atoms, okay, atoms taking place in this situation. Okay, what I mean is, when I have taken a combination of atoms, all of them behaving differently in a groups, so that is going to create me some kind of a disorderness. Now, that disorderness is actually captured. You see now, the disorderness is captured inside the rho total. So, using the rho total, can we represent the entropy? Of course, yes. There, okay, like advantage where density matrix formalism, or else a density matrix formalism. Okay, what is that is? You take the density matrix, rho total, you multiply with its log of rho total. Okay, basically you are doing a matrix multiplication of same order. Probably you may end up with a matrix of some size, and you find the trace of that matrix. Okay, you take a negative sign of that matrix, that is going to give you a von Neumann entropy, which is just an equivalent to a Shannon entropy of a random variable. Analog, I'll say analog. Okay. Now this is best suited for, okay, for quantum information, because we are talking about the density matrix representing quantum systems. Okay, right? Okay, fine. Now remember to put the subscript to T total. Okay. Now, as per my presentation, if you see, okay, let me go. You see, this one Neumann entropy, it quantifies the mixedness or the measure how mixed the system is, how uncertain the system is the moment it mixes up. You see, that is a very powerful mathematical statement which captures the density matrix information into a, and in that way it will address uncertainty in the system. Okay, very good. Well, let's see in some scenario where, let's say, the system is pure. Okay, let me get back there. Okay, few cases, or you can say discussion. Okay, discussion. What is the discussion I want to have is, let's say, okay, let's say I have the all of them individually behaving like psi 1, psi 2, psi 3, psi 1, psi 2 up to psi n. Luckily for me, by some means, psi 1 becomes same as psi 2, same as up to psi n. Basically, let's say it is equal to psi. All are behaving same way. In that case, what happens? You see, the row total from the above is, okay, is just simply row, which means what? The trace of row total is simply trace of row. Not only that, you remember, the trace row square is just a trace of row. You know why? Because row square, any density matrix you take square root of that is actually the same. You know why? You just take a density matrix which is equal to outer psi outer. When you square, what you get? What you get? You get, okay, this you get. Anyway, there is inner product is equal to 1. So I end up with the outer product with psi, so I'll get rho. So density matrix square is rho square is equal to rho means the quantum state, if it is pure state, so only cross check you can do is, okay, check for rho is equal to rho square. If yes, then it is a pure system. Means everybody plays in the same way. Let's say they are different in the sense all are individually of their own kind, means if the density matrix is maximally mixed. What is the maximally mixed? Let's take a density matrix which is alpha absolute square, alpha beta star, beta alpha star, beta absolute square. If you just to take, let's say there is a density matrix, there is a chance of getting equal chance of half, equal chance of heads and tail. Let's say I don't have any polarization. Okay, what is the polarization mean? In the case of qubit, electron being hopping between ground to excited continuously, okay, that kind of a polarization, it's like a ground state, the atom is there, nucleus is there, electron is there. Sometimes it is very close, sometimes it is very far. So that is a polarization for you. So that kind of a polarization far and close, if that kind of situation is not there, so it's like a simple fair coin, either head or tail if I have. So that is called a maximally mixed system where rho is simply identity by 2. Okay, so in this case, if you just to try to find what is one Neumann entropy of rho, okay, I'm sorry, In this situation, I will get, depending on the dimensions of the system, I'll simply get, here in this case, I'll get a log of 2. Okay. How? I'll show you now. For this particular situation, minus trace of, okay, I by 2 log of I by 2. Okay. Log of I by 2 is what? Minus trace. Let me explain. 1 by 2, 0, 1 by 2 into log 1 by 2, 0, log 1 by 2. Now, if you just find out the overall expression, overall the matrix, which is half into log 1 by 2, half into log 1 by 2. If you just trace of this matrix, you will get minus trace of, okay, trace of this. Let me get rid of the trace, which is simply log 1 by 2, okay, which is minus of log 1 plus log of 2. So minus of log 1 is 0, so which is log of 2. So binary situation, this is the case. For any d-dimension case, let's say for any d-dimensional system where rho is, okay, d by d, there the one Newman entropy of that system, okay, rho of t is simply maximum situation of d. Okay, we got that. Okay, let me jump quickly to the presentation. So we are losing a lot of time, so we have to go a little bit fast. Okay, what is the properties of this von Neumann entropy in the case of our quantum information? If you see, okay, it has something called unitary invariance. This von Neumann entropy, it is not going to change from, okay, if there is a system which has undergone some change, a quantum variation, okay, so that for us, you know what, let's say there is a quantum state which undergoes some unitary change. So how do I represent new quantum state? Rho prime. Rho prime is simply unitary acting on rho, left and right. So left I have unitary and the right we have unitary dagger. This is what the unitary transformation of a quantum state. You know how did I got? You go back and see if there is a quantum state on unitary action, it becomes psi prime, which is u into psi. Okay, what is the corresponding density matrices? Density matrix is psi prime outer psi. On the right, what I have? On the right I have is u psi psi. Okay, let me take neatly write that. Again at the bottom. So rho prime is psi u psi u dagger. Interestingly, mid one is rho. Okay, so I got that answer. So that is what I have. Now, if system undergoes such unitary transformation, interestingly, the entropy, the von Neumann entropy remains intact, not going to change. What I mean is, it is going to be rearrangement, but in an orderly fashion, rearrangement would take place. An example I'll tell you, if the students are sitting in, let's say there is a quiz or exam you are going to conduct. Okay, if you ask the students, please sit, okay, please sit in orderly fashion so that, okay, not too close, not too far, and ensure that, let's say you are conducting 2 exams, okay, in one desk there should be one exam A, another exam B. So you ask them to sit in A and B different exam guys in the same desk. Let's say they sat. you got a doubt. There are students who are sitting very close, some group of students sitting continuously one behind the other. So you got a doubt. So what you will do? You do the shuffling in orderly manner. So if you do that shuffling in orderly manner, not shifting everybody to one place or the other place, you're doing an orderly manner. So that is what the quantum kind of a transformation, where the entropy is remaining to be same even after doing a rearrangement. Okay. And another property is concavity property. Entropy increases when quantum states are mixed together. We had the same scenario in the previous situation in the classical information case. Here also it is happening. Okay. And next, sub-additivity. Additivity in the sense, let's say I want to find the entropy with respect to A and B. Okay, the two systems are there of composite systems here, and two systems are composite. Now, if you remember, when I take two qubits, when I go back and see in the previous case, quickly, okay, I was creating entanglement, you see, that case, I want to go back. Yeah, this situation. When I take two qubits, they may exist in the form of all the four possible cases. Okay, up to that, it is fine. The entropy of the system A and system B is just mixing up. The moment I create an entanglement by suppressing two of the probability amplitudes, here in this case alpha B and beta A, if I just suppress them, I am going to get an entanglement here. You see, in this case, after the entanglement is created, the entropy may be reduced. Okay, because you are creating some kind of a correlation, you are creating some kind of a interrelation, you are creating inside of some kind of a orderliness, means something happens there should trigger something else. So there's some kind of a orderliness you are going to create. With that, what happens? Entropy may become lower as you have a composite system where some correlations may be developed. So entanglement is an example. Entanglement. Okay. Now, strong sub-additivity. What is that is? If I have three systems now, system A, B, C, okay, right? And in this case, let's say system BC and AB, let's say A has some kind of a correlation with the B and C has some correlation with the B, so C as a B. In this case, because of their part by part correlations, if you just add the right two, that may not be okay equal to the entropy with all the three and the entropy with the mid guy who is having a correlation with the both B, A and C. So in this case, you may say the entropies may not be equal. In this case, the entropy may be slightly lower than the right side. This is called strong subadditivity. So what you can take is, let's say there is a system A, system C, and there is a system B. So system B has some kind of a relation with B, A, okay, and also C individually, right? So this one is SAB, this one is SBC, okay? So I want to write down what is the overall SABC and S of B only. So that is a the quantity. So this is going to be much less than S of AB plus S of BC. Very important. Okay. Right. Maybe I'll write down here. S of BC. Okay. So this is a fundamental quantum inequality, we will call it. Okay. And there is something called Araki-Lieb inequality. What is that is? Absolute value of the difference between the entropies between A and B system may be always less than or equal to the A and B together. It's a bound entropy differences. Maybe a particular situation if you just take, in that case you might come across this. As of now, you can just take it as an information. Okay. So if you see these properties reflect the unique structure of a quantum mechanics and distinguish one human entropy from its counterparts. What is the counterpart? The Shannon entropy. Okay, right? So in each case, if you go back and just cross check what is the Shannon entropy properties, these are the Shannon entropy properties. Okay, there are 5 properties. In the same way, we have seen one human entropy in the case of quantum systems or quantum information. Here in this case also we have 5 properties. Okay, okay, then let's see, right? Shannon versus von Neumann entropy, a mathematical connection. Okay, right? So we have how much time? Yeah, I will take a few more minutes and finish this off. Okay, so here if you see it, let me enlarge for your convenience. Yeah. When rho is a diagonal system, means I considered maximally mixed system. Rho is simply 1 by 2, 1 by 2. In that situation, okay, when rho is diagonal in some basis with eigenvalues, okay, some pj, some pi. So here if you see it's a diagonal matrix, the eigenvalues of this diagonal matrix you see this is going to be plus half. Okay, it's going to be half. The eigenvalues are half, which is actually pi is equal to half, means I is taking 0 and 1. Okay, in both the cases, the eigenvalue is half. In that case, what you see is the von Neumann entropy, interestingly, comes out to be exactly same as the Shannon entropy. Okay, so in the Shannon entropy, I was using earlier variable x. You see, I was representing von Neumann and Shannon entropy of variable x. Here I can also say h of p of I. Okay, and s of rho is equal to h of pi. What is pi here? Is a probabilities. Okay. When von Neumann entropy and Shannon entropy happen to be same, when I have a system where the quantum density matrix is a diagonal matrix. Okay, so in non-diagonal, sorry, it's not a non-diagonal matrix in that case. I'm going to have absolute alpha square, absolute beta square, alpha beta star, beta alpha star, which means I have a polarization in the system. Okay, 1 minute. Okay, if I have a polarization in the system, in that case, what happens? I am going to have a non-diagonal element. So the rho is not diagonal. In that case, I cannot say S of rho is not equal to H of pi. I can't say that. Okay. So in the text form here have Shannon entropy, entropy of probability distribution. Entropy is a entropy of probability distribution. Von Neumann entropy is entropy of quantum density matrices. Okay, classical entropy, Shannon entropy is a classical random variable random variable case. It deals. On the other hand, von Neumann entropy is quantum state vectors. Okay, so x and y and all the random variables are commuting operators. Okay, but in the case of density matrices are not commuting, non-commuting observables are also there. The unitary operators are non-commuting, means x into y may not be equal to y into z. Sorry, x into y is, okay, sigma x and sigma y, right, is not equal to sigma y into sigma x. So matrix multiplication is not commutative. Okay. So in the classical case, I have a deterministic measurements, means if I measure, I will certainly get one particular object for particular case, a particular value. But in the case of quantum, there may be a probabilistic in nature. Okay, the chances of getting 0 or 1, okay, is probabilistic. Okay, P1. So that is a different gameplay. So von Neumann entropy provides a natural generalization that reduces to Shannon entropy for classical probability distribution. That means when I get rid of the quantumness by getting rid of the polarization terms, I will get that. So what I mean is alpha beta star, beta alpha star going to 0 implies S of rho becoming H of pi. Okay, that is what the final statement here. Okay, and the last slide for today is, if you see, entropy and the information gain. Information represents the reduction in the entropy. Okay, the fundamental connection between uncertainty and knowledge acquisition. If you get more knowledge out of the system, and if you get to see there is less disorderness, then you can accordingly you can say, right? So let's say there are mutual information I want to write down. So mutual information between, there are two variables x and y. So mutual information between x and y is simply equal to the entropy in x plus entropy in y minus entropy in x for x and y together. Okay, right? X and y together. This is just like, there is a Venn diagram, x and y. So right, if you just remove this multiple times, you are going to add, when I take x and y together, so you are going to get a mutual information. So that is what you have here. Okay, so the quantum extension is replace the Shannon entropy, okay, with the von Neumann entropy for a quantum system in this case. Okay, right, replace h of x and h of y with rho of, let's say, rho with respect to system A, right? Let me remove that. And rho of system B, and which is S of rho B, right? So accordingly, you'll get mutual information with the system A and system B is von Neumann entropy of system A plus von Neumann entropy of system B minus von Neumann entropy of A and B together. Okay, so that is what say quantum extension. Okay, beyond classical limits, quantum entanglement enables mutual information beyond classical limits. That's what we saw. The entanglement is not a small thing, it's a very, very powerful thing. It conveys more information, more capable than classical information. Okay, key takeaway here, quantum systems can exhibit correlation and information sharing that fundamentally exceeds the classical limits, opening a new frontiers in the information processing and communication. That's why everybody is after quantum communication. Okay, right? And this framework bridges classical information theory with the quantum mechanics, providing tools for quantum computing and cryptography and communication protocol. Both Shannon as well as von Neumann entropy together, which gives a mathematical interpretation for us. Okay, right? So I will just share these notes and also my hand notes for you people for understanding I was planning to even go beyond. What is that beyond is? Okay, let me go and show you. There is one more PPT also I prepared, an extension, an application of quantum channels in terms of entropy. So I wanted to discuss this, but we just ended up with the first part only. For your understanding and extended work, what I will do, I will share the second part also. This is about another 9 slides or overall 10 slides. You can go through it, but for the quiz I would not include. But remember, as per the case of the schedule, I was asked to give the quantum digital communication prospect in terms of Shannon entropy. I gave that. Shannon entropy is a classical entropy. In the case of quantum, it's a von Neumann entropy. I connected both of them. And if you want more insights, you can go through the second PPT also. Okay. So there are some discussions also in terms of mutual information, in terms of bipartite systems, means multiple, let's say 100 atoms I've taken, groups I will make, two groups. There is 50 here, 50 there. They call it as a bipartite system. In that case, what is the entanglement and all those things I did. I just made some kind of a small descriptive PPT. Okay, you can go through it and understand. If there is anything, you can always come back to me. All right. So, like Arka sir was mentioning earlier, so time being, this is that's all from my end. So I'll come back to you people on 15th and 16th, if I remember correctly. Okay, 15th and 16th, and then I will continue the statistical physics parts. We did up to Gibbs principle, thermal equilibrium by Gibbs principle, and then we will go on to do something called Bose-Einstein statistics and Fermi-Dirac statistics on 15th and 16th. So till that, have a nice learning, happy learning in this QT02. Okay, so I'll hand it over to Akka sir. Sir, please take over.
Okay, sir. Thank you, sir. Thank you very much. I think students have really enjoyed this, although they're in the holiday mood, but we can see the involvement here also. So thank you, participants, also for being so much attentive during these holidays, and thank you for being with us. And thank you, sir, once again. I think our 4 sessions with you are over now. Next day we'll have continuation of this topic, but with another speaker, Ritajit Majumdar, will have with him. By the way, sir, kindly share the questions with
Yeah,
over
sir.
you.
I just see few questions here. Maybe I'll
Right.
quickly round it off. Yeah, I think 427 Rajeshri is asking, in chain rule, why is the main controlling event right, sir? Yes, depend what variable dictates which variable is a question. Let's say I toss a coin. Depending on the coin output, I decide whether to go for the dice rolling or not. So here, the coin tossing is the main variable. Okay, accordingly you can see. Okay, next question is Valli Kumari is asking at 451, can we have multiple qubits to one qubit entanglement and vice versa? A beautiful question. Okay, multiple qubits to one qubit, of course, yes, right? So we did had this kind of a situation where A, B and C, three systems were taken. Okay, let me show you that example which we had. Okay, quickly I'll just where is that? Yeah, I did draw that. 1 minute. Okay, it was there on the presentation itself. 1 minute. Okay. Yes, so here in this case, okay. Yeah, here you see A, B, and C. See, B is entangled with A, and B is entangled with C, but A and C are not, B and C are not entangled. So here two qubits A and C is entangled with the system B, one qubit. So answer to your question, Valli Kumari ji, yes, we can have multiple qubits to one qubit entanglement. It's possible, and vice versa. Okay, so you can just generalize for any situation. And the next question is by Naresh 9459 is asked, what is the application of entropy in both classical and quantum information system? Very good question. That would conclude the entire discussion today. See, when I want to process an information, I want to use some kind of a data embedding. Okay. So if I want to add 2 and 3, and paper I can add. If I want to add a large digit with another large digit, I need to have a paper. If I don't have a time, I will use some machine. How the machine does? It wants to understand what you are giving. So I would use some binary conversion. So while using the binary conversion, I embed the information into the digital hardware. So there, how much information I embed, while embedding the information, is there any problem? Is there any issue with the system? In that way, in that case, the orderliness is actually impacted. So how much orderliness is impacted, we should able to address that. So for that, you are going to use the entropy as a measure to understand how tactfully, how perfectly I am going to embed the information, how perfectly I'm going to process the information. So in every step, you can calculate that particular the perfectness using this entropy. Doesn't matter if it's a classical or quantum. Basically, you're processing the information. At that case, you need to have this kind of a quantifier or a measure. Okay, right. Again, Pushpak Yadav reiterated the question, I think, from Naresh Ji. What is the application of this entropy in both classical and quantum? I did answer. Okay. In information theory, entropy is a measure of information. That's what he gave one answer. I think he's correct. Okay. And Prasanna asked about 5 o'clock. What outer product is equal to density product? Okay, let me correct. The density matrix is actually equal to the quantum system outer product. Okay, right? So you are saying density product. It's not the density matrix multiplying to density matrix. Probably I'll get something else. If it is a matrix multiplication, it's a matrix multiplication, I'll get something else. If it's a mixed system, you see row mixed, I'll get a row mixed square. Remember, the trace of row mixed is 1, by the way, but trace of row mixed square is not 1. Okay, so we cannot say the quantum outer product may not be density product. Okay, right? So remember, just rho is density outer product. Okay, so just that small distinction you should know, Prasanna ji. Okay, so any other question? Yeah, that's all. Thank you so much for very interesting, valuable questions. I'm going to add the whatever answers, density matrix. Okay, thank you. Yeah, see you in the mid of October. Okay,
Yeah,
Akash,
thank you,
please
sir.
take over.
Thank you, sir. We'll meet once again on October 15th and 16th. And students are actually waiting for you, will be waiting for your sessions. Right? We have seen that they're enjoying your sessions like anything. So thank you, sir, once again. And thank you, participants, for being here with us despite of the holidays going on. We understand that. So again, let's talk about it. One more thing, some people are asking about the quizzes, quiz 1 and quiz 2 and 3. For that, just I will inform you. After few more modules, we'll announce the date of quiz 2, and then again for the last few modules, we'll take the quiz 3. So we'll announce the dates. Don't think that it will already be there. Only quiz 1 is there. Quiz 2 and quiz 3 will announce at least 2-3 days ahead of time. So thank you, everyone. Thank you, the participants. That's all for today. Let's meet tomorrow once again with continuation of this topic. Okay. Bye again. Bye, sir.
Bye bye. I'm uploading to the Converser. People can check.
Sure.
Yeah, somebody
Thank
was
you, sir.
asked for a reference. The reference is Preskill notes I used for this. I'll upload the press skill notes chapter 5, which is the reference for us. I'll upload that also. You can just check if you don't understand my notes. Okay, bye bye, see you.
See you, sir.